I think we're going to have a discussion now. So for whoever still has the strength to stay around. Vikas and Shumon will take over with a very quick summary of some of the main ideas we saw throughout the talks. And then, whoever among the speakers is still here is very welcome to stay as much as they can or want to. And we'll open up the whole, anyone should be able to talk in this session, and we can just have a kind of an open-ended discussion. And then, of course, if there are questions for Aaron, you can ask them in about 2 minutes after Vikas and Shumon give a summary. You can ask questions of anyone. So Shumon.
Yes, let me share the slides. Can you see now?
Yes, we can see.
All right. Yeah. So yeah, I also wanna appreciate all the speakers from myself as well for today's workshop on safe road control with running. We acquired a lot of knowledge and potential new research ideas throughout today's talks. So I want to briefly make a summary of the today's talk from 8 speakers in total. So the first, we had a talk by the Professor Dimitra Panagol. She talked about the fixed time control Lyapunov and the control barrier function formulation, where the both the stability and safety can be achieved in a prescribed finite time, regardless what is the initial condition is. That at least for me was very impressive in terms of the introducing a new concept, fixed time, the safety guarantee, and she also made some adaptive method under the unknown dynamics. And for second talk, we had a presentation by Kelsey Aaron. She talked about the reparameterization with respect to the mode transition. And that was also very impressive in terms of the intelligent running method for robotics task. And the next, we had a talk by Sergey Revin. He essentially presented about the reinforcement running method, both on policy and offline method. And especially as the safety constraint perspective, he talked about the conservative queue running for offline RL, where the conservative queue function is kind of the optimizing the lower bound of the queue function that brings up a new idea, and incorporated in the safety constraint using the failure rewards. And the next, we had a talk by Professor Marco Pavone. He talked about the robustness of the autonomy stack in terms of the probabilistic performance-centric planning reachability method. And he also talked about the random dynamics first in a stabilizable model, and developed the running-based control formulation and Lyapunov function. And in the next talk, we had a presentation by Professor Rose Yu. She talked about the running the complex dynamics such as the fluid dynamics using the idea of the symmetry, where the tool is from the graph-based, or no, the group theory, where the group is called the G equivalence, which satisfies some conservation law of the model. So she presented some theoretical results and the simulation results for her work of the neural network model with incorporated symmetry. And next, we had a presentation by Professor Melanie Zeringer. She talked about essentially MPC, model predictive control, and she brought up several new ideas for me, like the Bayesian MPC and the soft constraint MPC, where she also incorporated the idea of the learning the dynamics and the uncertainty of the model. And next, we have a presentation from Professor Kratomlin. She talked about the reachability analysis, reachability set propagation from the fundamental technique, and showed some real implementation in the mobile robot with depth sensor, where the reachable set can be computed online with associated with LQR control that brings us a new idea. And at the end, we had a presentation from the Professor Arnold Ames. He talks about the CLF, CDF, QP formulation for satisfying both stability and safety. And especially under the uncertainty of the model, we have an idea of the modifying the CDF constraint with bounded uncertainty of the dynamics. And he showed several implementation in the rect robot. So let me switch to the BICAS now for the open problems and future perspectives.
Thanks, Shumon. Can I share my screen?
Yeah, or I can just
okay.
move the slides when you want.
Okay, so right now. So anyone can ask questions right now. So everyone's mics are in their control. They can turn on their mics. So I'll just start with questions for the panelists. We'd really like to know your each of you or whoever wants to answer perspectives on these questions. Like learning full dynamics of a robot is hard, as Aaron pointed out, it's high dimensional. So one approach to go is that you can project the dynamics into the control barrier function or stability or multiple domains that we care about. But in case of like safety functions in a real robot, it would be very hard to get data samples on the unsafe side of the spectrum. So how should we go about that problem? And what are the other main challenges that you see going forward? What are the open problems? And what are the interesting directions that you see emerging? With that, the floor is yours.
I'll kick it off really quick, since just obviously my perspective is to project the dynamics down. That's pretty clear from my talk. I think there's a lot of benefits to that. I think what you pointed out, though, is a very important point, which I want to stress, is that, I mean, in the end, the real challenge is bounding uncertainty and understanding uncertainty and what it means and what it looks like from data. The problem is your understanding of uncertainty depends on where you are. So if you, as you said, if you can't go unsafe, if you don't, the only way to really learn about the boundary of your safe set is to go to the boundary of your safe set, but that could be a really bad idea. So it's this exploration versus exploitation kind of trade-off phenomenon, which is how do you sample in your space to get a good picture of what's happening with your uncertainty, but in a way that doesn't actually make your system unsafe in the process. There's a tension there that I think is kind of the root of a lot of the challenging problems.
To follow up on that, I would like to agree with what Aaron said, and maybe the answer to whether you should allow yourself to become unsafe depends hardly on the depends exactly on the application, and fundamentally on the application, in the sense that you might not want to lose a single big robot, like you might not want to cause harm to a single expensive robot, but it might be fine if you have a swarm of small robots to sacrifice one of them for the sake of obtaining knowledge for the rest of the team that is going to improve their chances of accomplishing the task. And of course, that brings also way more other questions on, okay, if you were to sacrifice someone, then who do you sacrifice and how? But essentially, in order to do this exploration and exploitation cycle, unavoidably, you have to expect that you might end up sampling from the bad part of the state space. So if you can afford to lose that agent, then that's fine, probably. So I would like just to comment on that. Maybe there is not like a single answer that fits all applications, but rather this has to be considered, has to be determined based on the application that you have at hand.
Thank you, Aaron. Thank you, Dimitra. Any different perspectives? Or the second question, what are the open challenges?
I just wanted to say that I agree with what Aaron and Dimitra said, because you can imagine for like an air traffic control application, that's, that if you're learning, what are the opportunities to learn there? You're typically learning about, wind behavior at different altitudes. And that can, that's actually something they do. Pilots will kind of go up and sample it and then provide information to air traffic control and other pilots around. But it's very conservative. Whereas I think, if you were learning a policy, a robotic system that's learning a policy to interact with somebody, perhaps there's, perhaps it's okay to be maybe a little more aggressive, if, as long as it's not going to hurt the person, and scale back. Perhaps, there's some more give and take there. So I do think it depends on it depends on a number of things, right? It depends on the application. It depends on the way that you're representing the model and the safety constraints as well. Whether or not you're doing that in a deterministic way or a stochastic way. It sort of it depends on whether or not you're okay with a sort of probability of going unsafe, all of that. But I think it relates back to the application. That's the biggest thing.
Do you think there's an opportunity for transfer learning of safe sets? So this idea came to mind when Dimitra mentioned the idea that you could have like expandable robots. Do you imagine a situation in which we can learn kind of safe unsafe set on a cheap or safe robot and transfer this to a more complex system? I imagine the system dynamics play a big role here, but also I think learning about the environment could be possible. I think it's something interesting to consider. I don't think I've seen kind of any work in this direction.
We have a project with it's like a nuclear, it's with the nuclear engineering department, and there's a kind of exploration phase to see whether or not there are active nuclear sources. And so there's actually kind of this, cheap robot that's doing that's sort of navigating and also sensing in the environment in a kind of quick pass before the more expensive sensors go in. So, I think it's something that it makes sense in a number of applications.
Yeah, I think that's really interesting. Any thoughts on
I think, really just one point. So I think absolutely this is a great question. I think the point of projection isn't necessarily to barrier functions or anything in particular. It can be to the environment and to the force interactions, right? So there's lots of low dimensional ways to quantify data you're collecting, right? Or lots of ways in which data can enter the system. And it's that structure of not just learning everything, but learning the way the data is coming in. For example, you could, if you want to talk about transferability, you could talk about, well, if I'm learning about walking in different terrain types, I could learn the ground reaction forces. And specifically, I could learn parameters of granular media models, right? So you can create some structure there and then learn that. And then that would be hopefully transferable, right? So I think what I'm sort of advocating for is structure in what we're learning, whatever, and that structure will very possibly be application dependent, but ideally transferable if you capture that structure.
Yeah, one of the advantages I observed in learning, say, some of the dynamics is that you can exploit some structures like Professor Rose, you mentioned about like translation invariance or equivariance. So many of the robots or dynamics doesn't depend upon their absolute position, like unless it's about like wind disturbance or environment variables like friction. So you can utilize them, but if you're directly learning control barrier function or something like that, then you can't utilize that that equivariance.
Yeah, since you mentioned it, I also want to say that this type of idea of incorporated symmetry can be generalized to policy learning as well for control. There has been some papers, not from our group, but from Max Welling's group at U Amsterdam, where they apply the symmetry ideas to policy gradient ideas, right? Because, the idea is that in the cost function, there's actually some symmetry because, two different states can have the same cost, and that basically automatically translates to permutation invariance. So essentially that means, as just follow on what Aaron said, there's a lot of structure on redundancy, not only in a state space, which we leverage to learn better dynamics, but also in a reward function, and now we can utilize that to design better controllers.
Questions from audience?
Yeah, we can come back to the, oh yeah, there's a question. Claire, is a question for you.
Well, I kind of posed it as a question for everybody because I don't know how to answer it. But okay, so I mean, there's a lot of discussion about epistemic and allegoric uncertainty, right? And we kind of have a sense of what that means, but when I look at a perception module, like a deep learning perception module, I find it hard to even think about what uncertainty is there, or maybe, I mean, okay, I find it hard for myself. It's not my background, so I'm learning here, and it may just be that I'm not thinking about it the right way. But I haven't seen a kind of breakdown of when you look at deep neural nets that are being used in particular as sensors in a control loop. How does is there a kind of way to understand what is the uncertainty that's just always going to be there based on some fundamental, like the data that you've used to train it and the experience or context that you've put in it? And what is the uncertainty that's there just because you haven't done a good job of designing it? So I think until one of the things that I'm interested in doing is getting a much better handle on how to define uncertainty in these systems, so that we can kind of move forward with that. And I'd love any feedback or references or suggestions from the group here about this, because as I said, I'm a bit of a novice in this, but I feel like when we're designing, it's like we're kind of co-designing the learning component with the decision-making and control component, and how we co-design that is really important, and how we do those designs in parallel and how they interface with each other. So that doesn't really answer the question, but it's maybe asks it in a slightly different way.
Maybe I can take a shot at the first answer. So I should say first that I really agree with the question, with the idea that we need some uncertainty quantification, especially when we consider composition, because that's where kind of errors in one module show up and affect, like if you have errors in your perception, they affect the control side. And having some error bounds, I think Aaron also admitted that we need to think about those, even if we're doing a good job of estimating delta. So I think my perspective on this is that we can view a neural network as having two sets of inputs. One is your regular input data, and the other one are the parameters. So the way I think about it is that we have uncertainty in the X input and uncertainty in the theta or whatever the parameter name is. So we would need some way of kind of propagating uncertainty through the network, both in terms of X and also in terms of theta. And the question of whether this can be done efficiently is a big one. So I like the perspective on projection here, and not really trying to do it for billions of parameters, because the theta dimension of the neural network can be really, really large. So if we now start to, even if we keep some very simple form of uncertainty, let's say I want to store a covariance matrix over this, it's already infeasible, right? If I have 1 billion parameters and I have a billion by billion matrix, to just represent covariance might be impossible. But yeah, maybe thinking about kind of what are the important dimensions in the parameter space, or kind of just looking at the some subset of them when we propagate uncertainty could be a interesting question.
Yeah, I think. Oh, sorry.
Go ahead, Claire.
No, let me just respond quickly to that, because I think that what you're saying is absolutely right. And it's not that there hasn't been kind of a lot of work in people working in deep learning, for example, to do that, or to somehow represent that. And maybe it's too much to say it's a projection of that uncertainty into the output space. So looking at, the variance associated to the output and different methods like dropout for computing that. But kind of that breakdown into what is the uncertainty that you're always going to have, regardless of how well you design your system, and what is the uncertainty that you can minimize by, just like using the existing data, but doing like a different, having a different methodology for constructing those parameters. I guess I just don't have a good handle on that.
Yeah, I think this is, I was just going to say, I think this is a really central question that I don't understand very well, to be honest. I did do a little bit of work. This was actually work that was led by Sarah Dean at Berkeley, who's a PhD student of Ben Recht, on measurement robust control barrier functions. And I mentioned that in the talk, just like super fast. But the premise there is really this question in that, how do we bound the uncertainty? And more importantly, how do we determine where to go in the space and how to sample to bound that uncertainty provably? And at least under some uncertainty models, that's what we could do. Meaning, we didn't just learn the uncertainty and bound it, right? We rather determined based on our current uncertainty how many more samples we need to achieve a provable bound, right? So what I'm saying is there was a feedback loop there between uncertainty, our bound, and what actually went in the control system. And I'm just mentioning that because I think that's at a fundamental level what we'll have to start. I'm not saying using these methods per se. I'm not trying to put out my own work or anything, but what I'm saying is there's this feedback loop, and that's the essential part, is feedback between uncertainty and action, and where the actions, and then the sensors of course play a role there too, everything that was being said, but ultimately I think there's a very tight coupling there that we need to exploit. As control theorists, we should be in a position to do that. I mean, control theorists / learning people, to understand that loop.
That's a good point.
I'm not in, well, I don't know if am I speaking?
Oh,
yes.
we can hear you.
Okay, yeah, sorry, I wasn't sure how this works. So I'm not in deep learning myself at all, but from a distance looking at it, there's a lot of work on NTKs and whatever that may have come after that allow it to formalize it much nicer using traditional math. So I don't know if anyone here has more experience on that to see if they help with this aspect of uncertainty quantification.
Yeah, I guess I can comment on that. So I want to just answer what Claire asked before about uncertainty quantification. We actually just had a paper accepted at KDD about uncertainty quantification, deep spatial temporal forecasting, where we classified, kind of Bayesian-based UQ versus frequentist UQ. And frequentist UQ is essentially uncertainty on the parameters of the model, where Bayesian UQ is basically the posterior taking over that. So it's rather given a particular data set and do the posterior averaging. And they seem to be different, but we can kind of put them in a single framework through statistical learning theory. And the kind of the practical thing we did is essentially, characterize different type of UQ methods in the context of deep learning. So there's frequentist methods based on, stochastic Monte Carlo MCMC, based on Monte Carlo dropout, and there's frequentist method based on, jackknife, bootstrapping and stuff, right? So you can kind of look at two group of UQ methods on a very unified framework. Obviously, there's no definite answer which one is better. So that's why we did a more kind of benchmark study on this particular subject. And I would say the limitation right now is, one, we don't have the guarantee, as Aaron was asked. Two, we haven't published a paper about utilizing uncertainty for decision making, even though we do have a paper that just submitted to NERPS about that. So about your question that hit on the NTK. So what we found is that, using deep neural nets, especially when you map an input feature into a hidden states, and if you assume the features are approximately random, right? So in the context infinite wide neural networks, they're close to linear networks, and using uncertainty in the fitted features are actually much better than using the prediction uncertainty for decision making, if that answers your question.
Thank you, Rose. Thanks for the reference.
Sure.
Thank you.
Rose, as a follow-up, I was also curious, do you think that this kind of view of symmetry and manifold structure also provides a way to propagate uncertainty in much lower dimensions? If we exploit the symmetry, potentially we just need to think about uncertainty on the quotient manifold instead of in the whole space. I don't know if I've seen, I saw a really cool paper actually here at ICRA that was formulating visual inertial odometry on a quotient manifold, which made me think about your work. So I'm curious if you've thought about this.
That's an amazing question. So that's exactly the direction that we're thinking about. So there was a review paper from YET and about probabilistic symmetry. Actually, one of the classic methods in probabilistic modeling is what people call the Di Fernati theorem. it's about permutation symmetry, infinite exchangeable distributions. So the idea that you mentioned, leveraging symmetry to learn kind of probabilistic measures, is a great idea. Unfortunately, we haven't been able to publish anything on that, but I would say like the review paper by YET, and there's several papers about equivariant normalizing flows are great pointers.
This sounds really cool.
Thank you, everyone, for the workshop. Thanks, Nikolai and Vikas and Schumann for organizing this.
Thank you. I think I think it turned out really well. At least for me, it was a great day, and we made the decision kind of a few days ago to stream directly to YouTube, and I think that was a great decision because we'll be able to rewatch again if we. So I would watch a few of the talks another time because I thought there were a lot of ideas.
I want to echo that. Thank you so much for organizing this wonderful workshop.
Thank you to all the speakers. Thank you.
No, this is, I think this is a super important topic, so I'm very happy you all are bringing it to light and furthering the conversation. Yeah,
and thanks everyone for sticking around the whole day and having the discussion. So yeah, I think officially, I guess we are even 4 minutes after the end of the workshop, but anyone is welcome to keep discussing. You can stay on longer if you want to. I'm sure you can always email any of the speakers with follow-up questions. And yeah, feel free to email us as well if there's anything else we can provide. We're gonna keep the talks up on YouTube, and the contributed papers will stay on the workshop website. Yeah, we had a great day, and we're looking forward to kind of collaborations and continuing. I guess that's also the end of ICRA 2021. So I'm also hoping to see many or all of you in Philadelphia.
I'm in person, right?
Yeah.
Let's hope so.
Yeah, in person. That's the goal. We're gonna have a great venue there, so hopefully the virus doesn't interfere with that.
And hopefully you will have another version of this workshop also at the next ICRA. Continue, make it a workshop series.
Yeah, that's a good idea. I will be happy to do that.
Great. Thanks again. Great job.
Bye, everyone.
Thanks, everyone.
Thanks. Bye.